Hello, Shubhrab sir. Hello.
Hello. Hi, am I audible?
Yes, sir.
Hi, good evening. All right, I think we can start.
Hello.
Please.
Yes,
Hello.
Hello. Hi,
Am I
Manish.
audible, sir? Yeah.
Yes, you're
Uh,
audible.
Hello. Can
Hello.
Yes,
you?
you're audible,
Yeah.
Hanshu.
Okay. Okay. So I was. I wanted to ask some questions regarding in week 7. Like there is a one algorithm that we have, decision tree algorithm, right?
Right.
Huh.
Although
So
that was in an earlier week, but pick up
uh,
the question.
your voice is breaking actually. Can you repeat?
Yeah. Yeah. So decision tree was in an earlier week, but I can take the question.
Yeah, just a small question. So
Sure.
we have one parameter in that, like the depth. It uh, If we increase the depth, then the L- tree will, the model will get overfit, right? So it is a parameter that we compute, right?
Uh, mm, so yes. So
Using cross
max.
validation.
Yes. Yes. So the max depth, right? You can set it to something. So if you don't set a max depth, then the tree will grow unrestricted. In which
until it
case,
gets pure.
huh?
Until it gets pure, right?
Until it gets clear.
Yeah. So, but in MLP, I have MLP. So in MLP, I in the slides, sir had mentioned that the decision tree algorithm is a non-parametric algorithm. So uh, I thought that depth is also a parameter.
Right. So that is correct. So actually, it's not really so unlike let's say linear regression, right? So
Hmm.
for linear regression, the gradient descent is explicitly learning the weights. So if you think of linear regression as a black box, then gradient descent is explicitly learning the weights inside the black box.
Right.
Whereas decision tree is only learning the splits, right?
Yeah.
And you could say like the depth of the tree is one word for it might be emergent, right? It just happens to have certain depth by the end of the learning process, but it isn't explicitly learning the depth, right? Unlike the weights in linear regression. So in that sense,
So if I talk about the ridge regression, then we have a
yeah,
parameter called lambda. So
right.
that is also a parameter. So that also we don't learn, right? That is we are just learning the
Cross valid.
w.
Yeah, yeah. So the difference between this lambda, for example, the regularization penalty, it's a very good example. It's a hyperparameter. And hyperparameters are not learned in the same sense as the learning the weights for linear regression. Hyperparameters are chosen from. So the lambda, you define a set of candidate lambdas, right? And then you would use cross validation or grid search to decide from that. But there
So
is a difference. So one is like constructivist and the other is method of elimination. Right? Uh, yeah.
can you just uh, tell me the difference between the parameter and non-parameter? That will be really good. So, is that like
Different.
parameter and
Yeah.
hyperparameter? So,
Parameter and hyperparameter. So earlier we discussed this in an earlier TA session. So this is a good metaphor, I think. You can think of a machine learning model as a black box. You give it an input, it gives out an output. And the parameters are what are inside the box. So if you think of linear regression, the weights on the different features, that's what's inside the box. That's what sort of defines the input to output mapping, right? What, for a given input, what the output will be. Whereas hyperparameters sort of define the shape of the box. So there's something inside the box and hyperparameters define the shape of the box.
okay,
Uh, this, for example, this regularization penalty,
hmm,
the lambda in rigid regression or lasso regression.
correct.
The lambda is set before gradient descent is begun. So if you want to learn the weights for linear regression using gradient descent, you will first fix the value of lambda and then it will learn the weights.
Yeah.
Okay?
So it's outside from the box, outside the box, right?
It's
As you
outside
said.
the box, right? It sort of defines the shape of the box, as I'm calling it, right?
So my depth is
Yeah,
also a
a
hyperparameter.
hyperparameter, right? But yeah, but the way there is a slight difference. The way we have learned it, right? It's not really. So max depth can be a hyperparameter. Max depth, max depth, right, can be a hyperparameter, right? We sort of restrict the model from growing beyond that depth. But
Correct.
in general, it's not some. If we generally don't specify. If you don't specify a max depth, then it's not a parameter or a hyperparameter. Decision tree only learns the splits.
Hmm.
That's it. Yeah.
So what I got from this discussion is that the parameters means that the actual weights or anything that help me get to the prediction are the
Yeah.
parameters, right? And the
Essentially. Yeah.
the restriction that I impose on those parameters are
Hmm.
called my hyperparameters,
Mm,
like my in
sure.
regression.
Sure. That's one way of looking at it. That's not too wrong. But the most general thing, let me just try and maybe have some figures
Okay.
or whiteboard as the case may be.
Okay.
Hmm. Right. Okay. So you could think of, so what I started with earlier, you could think of as an ML model as a black box. So this is the model, ML model. So it's very often a black box. Right? So the most famous or well-known ML models presently, these neural networks, right? They are very much a black box. I mean, there are weights inside, but the input to output mapping is not very explainable. But just in general, let's think of it as an ML model as a black box. So what that means is it takes an input and gives out some output.
Hmm.
And there
Sorry,
is, yeah, Gagan?
sorry to interrupt. I
Yeah.
just wanted to confirm, as you mentioned that the input and output mapping is not clear. So can we understand parametric and non-parametric models as when the mapping is clear, like in linear regression, the mapping was
Yeah,
linear and it was clear, so it was parametric.
yeah.
And since in decision tree we do a lot of splits and nodes and leaves, the mapping is not exactly clear. So is it non-parametric in that sense?
Uh,
Decision
no,
trees.
right? No, right? I mean, decision trees are the most, like one of the most explainable models. Right? So decision tree, because it's like a sequence of if then else questions, essentially.
It follows
If
a
this,
path,
then
right?
that. Yeah. So it's the most explainable, the most like decision trees and KNN. These are the most explainable machine learning models, at least among the ones that we are learning.
Okay.
Yeah, but this parameter and hyperparameter, right? So let's just start with this machine learning model, often a black box, and there are these class of algorithms. These are called solvers, which you might be seeing in NLP. So these solvers, right? They learn the model, they learn the parameters inside the black box. So they learn the W.
Hmm.
But there are sort of think of this sequentially. You have a data set. Okay? You load the data set into a linear regression model, and then you do dot train. You know? You do like something like this model dot train.
Dot fit maybe in MLP.
Dot fit, yeah, yeah, exactly. Yeah. So in SQL it's NLP. But the model that you load it into, right?
Mhm.
That is this box. Sorry,
Correct.
that is this box. Right? So what I'm talking about, the hyperparameters. Right? The hyperparameters are here, sort of deciding the shape of the box. So what that means is that if before you ran model.train, right, you'd fix some value of the regularization penalty, right? Gradient descent won't learn the regularization penalty lambda. You would fix some value of the regularization penalty and then you'd do model.train to learn the weights, right? The
Correct.
best weights given that regularization penalty. So the lambda here fixes the fixes the model which you load the dataset into. Agree?
Yeah.
And if you wanted to learn the lambdas, right, for this you would use this cross validation or grid search
Correct.
essentially,
Yeah.
and that's it. So this
Okay.
is a good way to think about it, right? In short, sort of the parameters are the things deciding the configuration inside the box,
Okay.
whereas the
So
hyperparameters decide the shape of the box.
so when I say the decision tree is a non-parametric, means it doesn't have
Yeah.
like it has a hyperparameter, but it's not have a explicitly we don't have a parameter there.
Yeah. I guess you could say that.
Okay.
I
So
mean, you're sure about this statement that decision tree is non-parametric because the way I am seeing it, it is
yeah,
still learning the splits, right? So it is still learning so each question is of the form, feature, comma, threshold. So it is still learning these. For
yeah,
example, it's learning the threshold values, the threshold values which give the best split, right? The most informative split. So it does not exactly, I wouldn't exactly say that it's non-parametric. I hope maybe you can
uh,
agree.
yeah. I also thought that it's not
Yeah,
a non-parametric, but the slides is saying that it's a non-parametric.
perhaps.
I can show you.
Yeah, okay.
Second. Yeah. Can I share my screen? Hello. And I'm not allowed to share my screen. So I think you are mute, sir. Hello.
Yeah. Himanshu, if you have the slides in a Google Drive folder, then can you share the link?
Oh, okay, okay. I can share. Yeah.
Sure. Yeah.
Yeah. I'm sharing a link in week 9. The, yeah.
But Himanshu, this initial question is clear, right?
Yeah,
The
yeah. This
difference between the clear, right?
hyperparameter and her parameter is clear. Yeah.
Okay. 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 Yeah.
Yeah, I shared the link
Right. So where can I
in
find the file? Week,
week 9.
week nine.
So if
In
you
the
could share the screen.
Yeah, sure. So in week 9, the folder, I'm in the folder. So logistic regression or perceptron?
uh, just
You
wait.
said week 9, right?
Yeah, week 9. Yes.
So there are only two files here: logistic regression and perceptron.
Oh, wait a second. I think I wrong. Wait. I must have sent you the wrong link. Sorry about that.
I
Yeah,
think
possibly.
you're talking about MLP slides, na? It's
Yeah, yeah.
MLP slides.
It's MLT slide. Yeah.
Uh,
Just,
So
yeah.
you can see this YouTube link.
Okay. Yeah.
Yeah, here. I just shared.
Right. So I just saw these are this is from MLP, right? So mm,
Week 9 in decision tree PDF file.
yeah, yeah.
In the second slide, it's mentioned that it's a non-parametric supervised
Right,
algorithm.
right, right. I saw that. So I'm not exactly sure. Perhaps there is some alternate or more rigid or rigorous definition of parametric versus non-parametric models, which I'm not aware of currently. But yeah, just think about it and perhaps look it up in your own time. But it makes it. In conclusion, it would make more sense to me to call it parametric because it is still learning. For example, the thresholds, right?
Yeah.
In the questions which give the best fits, the threshold theta.
The
So those
questions can
can,
be
yeah,
called the parameters, right?
I think like sir, we
yeah,
have
sort of,
the splits in the tree. Can
yeah.
we call them like these are parameters? The splits.
That's that's what I was thinking, right? So it is learning. The KNN is proper non-parametric. There is no doubt that KNN is
It,
non-parametric,
it
right?
does
No
not
doubt
learn
about that.
any. Yeah.
It
Right.
does not learn anything.
So in that sense, decision tree should be non-parametric, na sir. Like in linear regression,
Yeah,
we have fixed like there will be linear relationship and we are calculating the weights. So that is parametric. But in decision trees, what we're doing that it will depend on the complexity of the data that how we are going to split and how many parameters we will have. Like we will have variable parameters that will vary as
No,
per the data.
but after training the decision tree, the question will be the same, right? As we saw in the linear regression, the W are also trained on the data, right? In the initial data, right?
So
They
so
also depend on the data. Right?
So it like we define these things like based on the training model. Na?
Yeah,
Every
correct.
algorithm after training will give the same thing. Like whatever the model we have trained, and after that, like whatever data we will give, we will like it will act from the trained model. But I think these terms we define like parametric or non-parametric. I think they should be from that when we are training the model.
Right. So, Alauddin, you're saying, I don't exactly get the question. So, you're saying linear regression has weights, right? The weights which give the best linear relationship, as you're saying. But decision tree is non-parametric because
Like I think it should be based on the parameters number, flexible parameter. Like in the linear regression, we have fixed parameters. We have fixed.
not necessarily. That is not very like. Anyway, this is going into sort of
Yeah.
more
Mhm.
speculative area. But I wouldn't say that just because the number of learnable parameters isn't fixed, they shouldn't be called parameters.
Yeah.
That's a bit anyway. Like I said, going into sort of off topic, out of the syllabus areas.
Okay.
But good question. Yeah, good question for sure.
Yeah. So if anybody has any, if I can
Yeah.
ask anything.
Uh, I've also from week 9. Like from which week you have MLP doubts or?
Yeah, no, I have doubts from this only MLT only, but yeah, that course is like dependent.
Mhm.
That's why.
I
All
had
right.
one basic from perceptron.
Yeah.
So,
Uh,
I wanted to clear one thing, like there was a situation when the data sets were lying on the y-axis on the boundary.
yeah. Yeah.
So, like exactly why since data set is linearly separable,
Yeah.
but still the perceptron will not converge. So,
So, so if all the data points are lying on the y-axis, you're saying,
two data points on the y and one was there on the first or second content. So I have this. I have sent you the screenshot on the G space chat.
right? Let me look at. Okay. Yeah.
So if you could share that so that everyone can engage
Yeah.
with.
Just give me 1 second.
So in the lecture, professor took this example, and
Yeah.
the first thing I was getting doubt in my head that the line that I drew, the red line, the shining
Yeah.
red one. So
Yeah.
why this line cannot be a decision boundary for the perceptron? Uh,
So the separating hyperplane has to pass to the origin, right?
it has to be passed. Then the y-axis could be the separator. Actually, the
The
thing is that,
y-axis, correct, correct, correct. The y-axis can
but
is not in this case, but y-axis can be in general the separating hyperplane.
so in this case, in continuation to this, the professor
Yeah.
took this data sets, and at the end, it was proved that the perceptron is not gonna converge. So it's not going to converge means we are not getting any line that will separate these two classes.
Right.
But
But
what I
there is
think,
no, yeah.
Mhm. but
So
what
there
I
is no line. The separator has to pass through the origin. That is implicit.
okay. So
We we have, yeah.
if
Go
the
on.
condition is that it has to be passed, is it due to W transpose X, that MX? It has to be passed.
Yes.
Like
Yes.
how can we claim that it
So
is W
just
transpose X? No?
yeah, just let's switch over to the Jamboard ones.
Hmm. And one more thing in
Right.
continuation to that, sir. Even
Yeah.
if like we have considered that yes, it should be passed from the origin, then the
Mm.
line, the y-axis can be our line. It is passing through the origin. The y-axis can be the separator.
Correct. 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 So
In
earlier, in
Hmm.
the in an earlier session, right, you asked me ki if, for example, this is my, if this is my, if this is my So, sorry, I think the tabs is crashed here. Yeah,
Hmm.
it's okay. So earlier for this separating hyperplane, right? One second. Close. Yeah, this should be okay.
Yes.
Right. So Alauddin, I think was a technical issue because Jamboard will not load. This is, and there's some, as you saw, there's some error about WebGL or something, so it won't load.
Like
But
you just could
yeah,
share the screen and open Paint or something. That
so Paint is not how I'd like to do things, but let me see if I can walk you through the idea overall.
okay, okay, fine.
Yeah. So we saw earlier that the weight vector is perpendicular to the separating hyperplane,
Hmm,
right?
hmm,
Because essentially the weight vector is the set of all vectors which are perpendicular to the weight vector.
hmm,
That's definition of uh, the definition of the separating hyperplane, right? So the separating hyperplane is the set of all vectors perpendicular to the weight vector.
hmm.
Agree?
Yes.
Right? So vectors are generally taken from the origin, right?
Okay.
So that means that all the vectors, this set of all vectors perpendicular to the weight vector, this set will be of all vectors starting at the origin.
Hmm.
So therefore, the separating hyperplane passes through the origin.
And
This-
we take
yeah,
starting point from the origin. That is the reason that we take the initial W naught as 0, 0, na? When you are checking for the
doing
person
gradient descent.
in the
Oh,
person
no,
W.
no, no. That's I think more of that's I think like
Like I was also thinking
so
about that.
yeah. I
Like
mean
when we
yeah. When
start.
I
Mhm.
good question because actually, do you agree with this? We saw this in an earlier TA session. Just this, and I can move on to the next
Uh,
part.
mhm.
The separating plane is a set of all vectors perpendicular to the weight vector. Okay,
Perpendicular to the yet. Huh.
right? So that's how it's defined. And given we saw in linear algebra, we saw in Maths 2 that
Hmm.
if I give you a vector, then you can give me the basis for the subspace perpendicular to that vector.
Perpendicular. Hmm.
You can do that, right?
Okay.
So you could do that, right? When if I give you a vector, right, you could give me a basis for the subspace perpendicular to that vector.
Like mathematically, I'm not right. Like I can't
Right,
remember everything, but I'm getting the concept. Yes, we should have that. Visually, I can think of that. Yes, we should have
right.
that.
So what I'm talking about is, I think Jamboard use it. Yeah, there you go. So, so if I gave you like, I can only draw up to 2D, max 3D here. But
Hmm.
if I in general gave you like a vector like this, like a W, you could in general be able to give me the
This line.
basis for a subspace perpendicular to it, right?
Hmm, hmm, hmm.
So just recapping, for example, just quickly recapping. If I have a vector, some w is equal to this 1, 2, 3. Let's go through it real fast. Let's say w is equal to 1, 2, 3.
Mm-hmm.
So then, I want w transpose x. So I want my s, or separating hyperplane separator, is equal to
Then equals to 0.
all x, yeah, for all v, uh, such that
W transpose X greater than equals to 0.
uh,
V.
I want this plane, right?
Hmm.
So if I want this s, given this given this w, I want this s.
Hmm.
So I'll just write it out again. This w is equal to 1, 2, 3. Let me look at what W transpose V looks like. It looks like V1 plus 2V2 plus 3V3 is equal to 0.
Yes.
Implies that your V1 is equal to minus 2V2 minus 3V3. Is that okay?
Mm-hmm.
Hmm? And this implies that the how to say, the spanning set for S. I'll just say the spanner of S. Right? I wanted this S. Remember, I wanted the separating hyperplane, right? Characterized by this weight vector W. So the separating hyperplane is spanned by, right? It's spanned by basically vectors of this form. One second.
V1 minus 2, V2 minus 2, 3, V3 and V3.
Hmm. Hmm.
Mm-hmm.
Just give me
So
a second.
replace V1 now. Like with V2 and V3 we can spell.
Yeah, yeah, yeah. So basically, one second. Before I write this,
Mm-hmm.
so it implies that some vector x belonging to S is of the form minus 2v2 minus 3v3 v2 comma v3,
V2 comma V3. Hmm.
and this is the span of uh, minus 2 0 0 8 no minus 2 1 0
Okay.
and this minus 3 0 1. So the premise that I want to drive home is that, and just quickly move on to the next part, is that if you are given a weight vector W, right, then if you're given a particular vector W, right, in this case it happens to be a weight vector, then you can immediately write out the basis of the subspace perpendicular to that weight vector,
Mm-hmm. Yes.
right? And when it's the weight vector in the case of perceptron, the weight vector learned by perceptron, right?
Hmm.
Uh, the subspace perpendicular to it, which we just found in the next slide,
Yes.
right? The subspace perpendicular to it, that is the separating hyperplane. So in this case, this will be a plane in 3D, and it will be a 2D plane in 3D. That will be the separating hyperplane. Agree?
What was the last statement you gave?
The last statement was key if I give you a vector, right?
Hmm.
If I give you a specific, like a numeric vector, like the W here, you
Hmm.
can immediately write out the basis for the subspace perpendicular to that vector.
Perpendicular to that, huh? Yes.
And what that means is subspace perpendicular to that vector means that every vector in that subspace is perpendicular to the given
That W.
vector, that W. Yes,
Yes.
that's it. And that when this W, that W is the weight learned in perceptron, this subspace S, which you can write the basis for, that subspace S is the separating hyperplane,
Hmm. Okay.
right?
Hmm. Hmm.
That's it. That's it. So let that settle in for a second,
Hmm.
right? Okay. So what was the follow-up question? So I got into this.
That data
Yeah,
set, so we can have
yeah,
that
yeah, yeah.
separator in the y.
So yeah, so what? Therefore, like you know, the definition of the separating hyperplane is set theoretic. So the definition of the separating hyperplane is the set of all vectors V such that W transpose V is equal to 0.
Perpendicular to.
What? Yeah, perpendicular to W.
Hmm.
Exactly.
Hmm.
Right. But vector starts from the origin. Right. So that means that yeah. So vector starts from the origin, right? So it means that if there's a W here, let's say this is the W.
Hmm.
So then this will be, perpendicular to W. All the vectors. So this could be some vector V1. This could be the vector V2. This could be some V5 and so on.
Hmm. Hmm. Will be the span
So
of
it's,
that. Hmm.
yeah, yeah. And it's sort of, the set of all vectors uh, taken together is the entire. So if you, at any, so if this was, for example, plane in 3D, like we found earlier for S,
It could have been the plane, the set of all the vectors forming the plane.
exactly, right?
Hmm.
So earlier we found this S is the span of two vectors, two linearly independent vectors,
Hmm.
means that it's a plane, it's a 2D plane in 3D,
Plane. Huh.
right? So if you took a point on this plane, that's a vector that has a position vector from the origin, right?
Mm-hmm.
And that's it. So therefore, the plane can be defined as the set of all vectors perpendicular to W, the set of all positions perpendicular to W.
Like the W.
Yeah.
Yes, we are drawing that. Every point
Ah,
perpendicular to that will form the plane.
yes.
Hmm.
But this, yeah, but these position vectors are taken from the origin, right?
These are taken from the origin.
Huh. The separating hyperplane, let's replace the word vector with position. The separating hyperplane is the set of all positions, right? Such that, the position vector is perpendicular to W, like that. Okay,
Hmm. Hmm.
right? But positions are taken from the origin. Right?
Hmm.
Therefore, sort of, I not sounding very clear to me, but I hope it's at least reasonably clear to you. Separating hyperplane has to pass through the origin. Now, you could do a trick basically. You could pad the data points. We have also discussed that earlier. If I have a data point X, right, I pad it with a dummy feature, one, a
Mm-hmm.
dummy feature that is one across all the data points.
Hmm.
And this essentially shifts it into a higher dimension. Right? This adding this dummy feature, if the data point was in R5, this essentially shifts it into R6. But
Hmm.
everything else stays the same, except that now the separating hyperplane can sort of not necessarily pass through the origin. Same thing that we did in linear regression. When we wanted to, yeah.
It will
So we can
allow.
always, yeah, yeah,
Actually,
go
it
on.
will give. It will provide an intercept to the separating plane,
Exactly,
adding
exactly.
the
Yes,
points. Mm-hmm.
yes, yeah. But
So like.
basically, it's like loosely speaking, if we went from R5 to R6, then the data points are now in an affine space, right? So it's like an affine, the data points are now in an affine plane of R6, right? It just means that if I went from R2 to R3,
Hmm.
right? So then the data points, so if X is in R2, right? This is in, sorry, this is in R3. After the padding, the data points are now in a slice of R3 because this is one across all the data points, right? Just think about it for a second.
Hmm.
It's like all the data points will be on that slice of the of R3 parallel to the XY plane. Z is equal to 1.
Z equals
But
to 1.
all, yeah, it'll all the data points will be on that slice.
Hmm. Hmm.
So this this now allows, this can sort of allow the weight vector to have like an allow for an intercept essentially. Yeah.
For intercepted.
Does that clear up your question? The
So, sir, how this is connecting to that? If I'm saying
your
that
question, right?
line, huh? Like, if why can't we draw our decision boundary that will be perpendicular to the x-axis, like just above the y? Like the data set that I provided.
Yeah.
So professor took that and he proved that perceptron is not going to converge in this data set.
Because once again, this it's not separable with a hyperplane passing through the origin, right?
So sir,
Yeah,
since it is xy, like with two features, we
yeah,
are in
yeah,
xy plane. So
yeah.
can't our line, which will be just above the y-axis,
Hmm.
can't it act as a decision boundary for this data set? That will pass
Uh,
the origin, na? If I will draw a line just above the y-axis, which will be the perpendicular to x,
just above the y-axis or just
yeah,
above the x-axis.
on the y-axis, if I
The
say,
y-axis itself, the supporting, we can
like
say the separator.
the vector could be w that
No,
I
but
the vector could be
mm,
that w, which is yellow
hmm.
one. So the separating plane should be
Good question.
perpendicular.
So you're saying the separating plane is the y-axis itself,
Huh.
and
Vector lies on x.
the tiebreaker is assigned to the green class
Huh.
or the positive class.
Huh.
Yeah,
For
that's what we do.
w transpose x greater than equals to 0. So for tie, we are giving that plus
Yeah,
1.
in which case, there's a thing, right? The linear separability does not guarantee perceptron convergence. You have to make stronger assumptions, this assumption of a gamma margin to ensure that the perceptron converges. But yeah, this, as you said, this is in fact linearly separable, and as you just rightly pointed out.
But I
But
think in
yeah,
sorry to interrupt. I think in
yeah.
hard margin it's like the for perceptron to apply, we should see that it should be linearly separable.
Yeah.
In hard
May,
margin, we don't see the supporting hyperplanes, right?
I have encountered some data sets where the
yeah,
data points were on the y-axis, exactly on the y-axis, and
yeah.
perceptron was classifying them.
So you have seen some actual data sets with, let's say, NumPy, sklearn.
Like on the actually on some of the problems, like I was taking problems from week 9, there are
Yeah.
some situations where we will have what I'm not getting is that here in this data set, if we are talking to the simple perceptron, the thing is that perceptron will converge or not is simply saying whether we are able to classify these data sets into two classes by a single line that should pass from the origin.
Right. I think I don't have an answer on this one. Uh,
So
Probably, yeah.
what I was not getting, that I'm repeating that again. My
Hmm, hmm.
question was that,
Sure, sure. Yeah.
of course, let's suppose I was drawing that wrong. That red line cannot be the line, since it should be a line passing through the origin. Since our decision boundary was W transpose X, so
Hmm,
MX
hmm,
y equals to MX, so it has to be passed. Okay, fine. It has to be passed. The red one is incorrect. So
hmm.
can't I draw the red one just above the y-axis, which will be perpendicular to X? That will also separate the greens and the red.
Right. So just one thing you're saying ki let's make the y-axis itself the separator.
The decision boundary.
I just this is a minor thing. You're above the y-axis, you mean on the y-axis, right?
On the,
So
yes,
that on the y-axis, make the y-axis itself the separator.
yes,
Yeah.
let's make
Yes.
the
So
y-axis itself as the separator. Yes.
yeah, I don't think I have an answer on this right now.
Yeah,
I'm
but
not.
when we
Yeah.
solve with the update rule, it doesn't come up to with the y-axis. But when we see that it's just by the diagram, it's like the y-axis should be the separator. It's just
Exactly. So when we do the update rule, follow the update rule, na, mathematically.
Hmm.
So since these data sets are on y-axis, so the perceptron is not converging. But visually, what we have learned that if we are able to draw a line
Hmm.
that is separating the two
Hmm.
classes, then
Hmm.
of course
Hmm.
the perceptron will converge. But in this case, the perceptron is not converging if you are going mathematically with the update rule.
yeah.
Right. I will have to look at that. Let's actually see what happens. So if I start with the zero vector, right?
Actually, professor delivered a line with this taking this
Yeah.
scenario that he was trying to teach us that the points are on the decision boundary or something. He was trying to
Hmm.
convey something, but I was not getting those things like the decision. Like even if the points are on decision or boundary, we can we can in this situation we can talk about something like tiebreakers or something, but we cannot say that we cannot classify like the
Right. Right.
was greater than equals to zero is saying that we are
Right.
handling the
Right.
tiebreakers.
Correct. Correct.
Hmm.
So why numerically, versus the red separator that you have drawn here is not a valid separator. I think that is established, right?
That
But
I
you're
was telling
saying,
you earlier.
correct, correct. And you're saying, ki, okay, if I make the y-axis, never mind this red line here. If I make the y-axis itself the separator, even then it should be, when it is separable, so perceptron should converge. But
Huh.
numerically, you're saying it doesn't. It
No,
doesn't.
mathematically it will not converge. Like if I can send you the
Yeah. Yeah, the
continuous.
worked out, if you have calculated it by hand, if you've done a dry run, then send me a picture of it. Yeah.
I'm doing that. So this is the first step. In the G chat, no? G
Yeah.
space.
Yeah. Yeah.
Uh, this is the first. This is the first step. Uh, Second one. This is second one.
Achha, hello then. I'll look at these calculations in a little bit. Please send them over and uh, I'll have a look at it. But just perhaps if others have other questions.
Yeah.
Sure.
If other
Yeah.
have, can
So
I ask
also,
you?
Alauddin, yeah, Alauddin, one last question. What do you use for
Sir,
these
I
notes?
want to talk about this just now. I
Actually,
co-pilot, and in that it is mentioned that when it is on decision boundary, it will keep
Yeah,
oscillating and it will try to find it. Like
right.
but the
so,
thing is that like why it is oscillating like
yeah, that's
visually.
what the co-pilot said. That if it is on the decision boundary, it will keep oscillating it.
So, actually, I was getting confused that what is then decision boundary? What is decision boundary then?
No,
It is
just
the
now you said
y-axis.
right the y. For regarding that only, I checked with the co-pilot. It said that it will
Okay.
oscillate since they are on the boundary. It won't find a stable solution.
So should all the sets on the boundary, should all the data sets from a particular class, if all are lying on the boundary, that is the case, or
Then you have to precisely ask to co-pilot. I
okay.
just randomly
So
check
that
and then it answers.
actually some of the questions I have found some data sets where the data points are on the x-axis
Mm-hmm.
and the perceptron has converged.
And the x-axis is the perceptron. I mean, is it a separator?
No, that
That's
time
what I'm saying. If it is a decision boundary, then it will oscillate.
Okay, so data points lying on exactly on the decision boundary.
Yeah, correct.
I think I have to like search more. Like if you are just talk about if we talk about decision boundaries, so decision boundaries will keep fluctuating, right? So in the initial, we were not exactly saying that yes, this is the decision boundary we will always take. Like we can have different decision boundaries, and this decision boundary was
Oh, right, right, right. Got it. So this it's because so it's essentially because all of them do agree on this that
Mhm.
so perceptron only makes a weight update if it misclassifies a data point. Right?
Huh.
Let's say like the second data point, and the jth data point in general, but let's say the second data point. Agree?
Mhm.
And then after a weight update, it tries to check whether it has correctly classified the same, right?
Again, it will start from the first data point, and it will check that, like not necessarily what it has updated on, but it will start again,
Right.
and may possible that it has disturbed some others.
Misclassified some others, you're saying.
Hmm.
Yeah. Hmm. Not quite sure, but I think, yeah.
Like,
Aladdin, yeah. Let me think about this for a while.
okay, fine.
Get back.
And if anyone has question, or I had some more questions till then.
Sir,
More.
sir, one question, please.
Hmm.
Sir, please take that question first.
Sure, sure. Correct.
Himanshu, go on.
Yeah, so in uh, in soft margin SVM, we have the penalty. We apply the penalty on the misclassified data points, and we try to uh, bring them on this separator, like
Yeah, yeah, yeah,
beyond the hyperplanes, right?
yeah.
So, and I also apply one parameter C, uh,
Hmm.
hyperparameter, if I say C,
Acha, which algorithm are you asking about? Is it
like support soft margin SVM,
It's
like
week 10, I guess, in
week
ML.
10.
week
Yeah.
10? Yeah. Let me not take questions on week 10 right now. Now, sure,
Okay.
if you can join in the next week, that will be great. You can just the next session will be on Tuesday. I'll look up my notes before that on SVMs and such.
Okay.
But
Yeah.
yeah, yeah,
Sir,
Uh,
maybe you can listen the question and then you can come up with your answer on
Yeah.
Tuesday.
Maybe in next class we can discuss that.
Yeah.
Thing.
sure. Now SVMs are a bit non-intuitive to me. I mean, SVMs are not very intuitive to me as of now. So anyway,
It's okay,
please,
sir.
yeah,
We'll come
Himanshu,
back
please,
on Tuesday. Yeah.
Okay. Yeah.
yeah, yeah. But Himanshu, please do share the question. Let me hear it and
Okay. So
yeah,
the I apply the epsilon will be my penalty for each data point
yeah, yeah,
that are misclassified,
mm,
and
mm,
in the optimization like objective function, I write
yeah,
uh, some regularization like C into summation of all the epsilons, right?
yeah, yeah.
So I want to know about the C. What does the C do? Like, is it a penalty? Is it a regularizer? Or like, what
It is the per unit penalty, right?
it is a penalty?
Per
So
unit. So if let's say the epsilon, right? The epsilon is how far it is from the decision margin, right? Right. So you want a per unit. You want to impose a per unit penalty, right? If it's 1 unit away from the decision margin, right? 1 unit away from the decision margin, then maybe 1 unit penalty. 5 units away, 5 units penalty. So, that kind of a thing. Or maybe you want the 1 unit away from the margin, 3 units penalty. 5 units away, 15 units penalty. Right. So it's the per unit penalty. So there's a bit of confusion there. C is sometimes the per unit penalty, and in sklearn, I think it's the inverse of that. So there is a bit of confusion, but C is related to this idea of a per unit penalty. Essentially, you would want on a you want to incentivize the model to make correct predictions, right? And as Sir says, you're then like the move going from hard margin to soft margin, right? You allow the model to have this bribery kind of thing, bribes. If it's on the wrong side, then it can pay a bribe and sort of get away with it, like that. So, you want to have like a per unit if a data point is very far away from the decision margin, right? You want to have like a per unit a per unit penalty which reflects that okay, this data point is far away from where it should be, right? In other words, the decision boundary needs to be readjusted because this data point is far away from where it should be.
Okay.
Tell me if that makes sense.
But I'm not able to
Yeah,
visualize that thing in the, like, if I draw the uh,
right.
points and the hyperplanes, and
Yeah.
uh, then I'm not able to
No, but
describe.
you agree that you know, you agree that epsilon is the distance from the decision margin, right?
Correct. Yeah. These are my
And you agree
bribes.
that, yeah, never. Did
Okay.
Sir introduce the epsilon as the bribes?
Yeah. In MLT, it's epsilon.
So in which case, let me just let me just look at that again. But based on what I understand right now, at least, your epsilon, if it's the distance from the decision margin, right? Then summation epsilon is like it's similar to the sum of squared errors in linear regression. It's the sum of the distances from the decision margin, agreed?
Mm.
Sort of, or the
Can,
sum
can
of the bribes.
can you come again? I missed.
No, yeah. What I'm saying is, if uh, actually, yeah. Let me take it up in the next session. That will be better, I think.
Okay. Yeah. That
Yeah,
will be
yeah.
fine.
Okay.
And one more thing.
Yeah.
When Arun sir was introducing week 6 in the lectures, uh, sorry, it's like a very odd week, so as we are
No, no,
in
it's fine.
week
It's
9,
fine.
yeah.
Go on.
But
If
like,
others don't have any questions to ask, it's fine. I can take it.
yeah. So
Yeah.
in there they have mentioned like one error term, like
Hmm.
W transpose X plus some
Hmm.
error
Hmm. Yeah.
would be our Y or prediction,
Correct.
and that
Yeah.
error follows the Gaussian zero.
So
Sorry.
actually, Himanshu, it's the other way around, right? So I would recommend you watch TA session that I did. It's available on YouTube, right? The TA session that I did this term.
Okay.
So you're not. It's a little bit like this. There is that error term. That error term is the noise, but it's not quite that the prediction is W transpose X plus the error term. It's that the true label is W transpose X plus the error term. In other words, this error term which follows Gaussian, this error term is there in the process which created the labels, the process by which the labels were created. So the labels were created, right? The W1, the Y1, the Y2, the Y3, they were created, right? Do you agree? The labels either by human annotation or or maybe scraping some online marketplace. The labels were created. Agree?
Okay. Yeah.
I mean, the data set has to be created, right? It's not going to
Yeah.
be there in nature. Agree?
It will be generated or maybe created somewhere.
Yeah. I mean, not going to be generated though, right? Mainly, you should say created. I mean, it's not like some natural outcome like sun rising and setting, right? The data set has to be created. It has to be collected. Agree?
Okay. Okay. Yeah.
Yeah. So the process by which the labels were created, right? The process by which the labels were created, they have some noise in it. That has some noise in it. So let's say the labels are this, housing market price of different houses, let's say. So The idea is that there is, for a given house, right, there's a stable price, there's like a justified, proper, correct price, and there are other like unstable or unpredictable factors which affected the price of the house on the day the price was taken. So it could be that it was a very hasty transaction. Something happened, and just the transaction, the house, transaction had to happen very hastily, right? It could be that maybe on that day, maybe it was a recession, maybe it was some other factors which we are not modeling as part of our data science process. Right? We are only trying to model the price of a house as a function of the area of the house, distance from the city center, number of rooms in the house, age of the house, etc.
Okay.
Right? So these other factors which were there, which affected the prices of the houses on the day the prices were taken. Right? These other factors are roughly grouped together as noise.
And
So the
they
stable,
will
yeah,
and they
yeah,
will affect my predictions also.
uh, they will affect my predictions also. Yes, kind of, yeah. But your this thing, it's assumed that this table, so the labels, right, the price of a house, it has a stable component and it has a noisy component. We we sort of set as a premise, and linear regression we set as a premise that that stable component, like the stable price of a house, the price of the house, if there was no noise, the stable
Mhm.
price of the house can be predicted as a linear combination of the features that we are looking at. So that's
Correct.
the W transpose X. The W transpose X is a linear combination of the feature values in X.
Mm-hmm.
Agree? And there is like a noisy component, and that the noisy, it's just, everything is grouped together in noise, and sort of the assumption is that, okay, let's say that this noise component follows a Gaussian distribution with some mean and variance, mean zero and some variance, and that's it.
So,
Yeah.
okay. So
So
it,
just to wrap that up, it's this linear regression as a maximum likelihood estimation problem. Right?
correct.
The epsilon term comes in once we think about the process of generating the labels as a noisy process. There is a stable signal and then there's noise. The stable signal is the stable price of the house. It's the W transpose X. And the noise is in everything else grouped together. That's the epsilon. And the assumption is that, let's just say that epsilon is a Gaussian with some mean and variance.
Okay. And that variance
Okay.
also,
Yeah.
like in below that, they explain some mean squared error, like, and that includes that sigma square into trace of x into x transpose inverse whole
Yeah.
inverse, like
Yeah. Yeah.
I said.
Yeah.
So like the
But tell me,
variance,
Himanshu, just clarify if the earlier question sort of you're a bit clearer on that.
I
This,
I thought I thought
yeah,
I thought because suppose I have a I have a true label.
right,
Suppose
correct.
I have a true
Yeah,
label 5,
yeah,
and if I predict if I get a W
yeah,
from all the data points,
yeah,
and I predict the prediction on the same data point, and I
yeah,
got 5.5. So
right.
the noise is what I got
Point 5.
is that epsilon. Yeah, is what I got.
Uh, Essentially, and not point 0.5, but it will be, uh, yeah, minus point 0.5. Yeah,
But as you are saying that
essentially,
this
yeah.
epsilon is not what I'm understanding, like.
This epsilon, so that minus point 0.5 deviation, the premise is that from from all the data points, right? If across the data set my prediction came out to be 5.5,
Uh-huh.
the premise is that the price of the house when I took it from the market, right? I collected the price from the market and I saw it was 5, like you're saying.
Uh-huh.
the premise is that the price of the house should have been at that time 5.5. And that minus 0.5 is the result of noisy factors affecting it away from what the price should have been.
So
Yeah,
it happens that if I took some data points in uh, other time period and some data points in like some other time period, and
yeah,
that's like, because all the data points will include my will help me to generate W, right? And that W will
yeah,
tell me the new predicted price. So you are saying that the the Y, that true Y is like
yeah,
I took a certain
yeah,
time period and I'm predicting based on the whole data set. So
right,
that was my the
right. So
website
you're
said.
so thinking about it in a time series context now. So when you're thinking about data sets collected at different time points, so there might be like some market drift where price of house price of houses on average have increased or have been decreased. So let's not think about the time series aspect of it. The data sets collected at different points of time, maybe 6 months apart or something. Maybe that's what you're thinking. But this thing, the true label has noise in it. That's the premise. The true label has noise in it, and if from all the data points collected in a single time period, right? If all the data points collected from OLX right now, right?
Mhm.
If I get the price of a house as, the predicted price of a house is 5.5, then the premise is that the true label, the price on OLX, actually has a noise in it, a minus zero point 0.5 noise in it, right? Which is, that's the noise is minus zero point 0.5, right? Which is, you know, uh, which is noise. So noise, what is causing that noise is a different matter, but it's noise.
So
Yeah,
one more thing, like y given x equal to w transpose x plus epsilon. So like what,
correct.
why y given x? Like is it and what
So
does it mean?
that's an assumption. So that's an assumption. That means that if I see a particular data point, right,
Hmm.
then the assumption is that the true label, so that's the y, right, not the y cap. So you're
Okay.
right. That's the y given x. So y given x is equal to w transpose x plus epsilon. This is a premise or an assumption that for a particular data point, a data point as a feature vector, right? For a particular feature vector or data point, the true label will have two components. One is the stable signal, which is actually expressible as a linear combination of the features. That's the W transpose X. The
Okay.
true label will have the true signal and the noise. So that's like a starting premise for this analytical decomposition into signal and noise, or
Okay.
stable and noise. Yeah,
So like
sort of. Yeah,
and this epsilon for all the data points will if I add, then I can say that this will be my squared error for whole data set. And is it
essentially. Yeah, yeah.
okay?
So you want finding like essentially finding the sum of squared errors. You could think of it as which basically which linear regression fit will ask me to call things noise the least, something like that. Yeah,
Okay. Okay, I'll watch the as you said
yeah,
like previous tier session, and I'll go through it again.
absolutely.
Uh, and sir, regarding the boundary, the margin we have in
Yeah,
perceptron.
yeah.
So in the tutorial section, I heard one of the line was delivered that the structure of the margin to be non-linear. So is it like is it non-linear by mistake, or
Structure of the margin for
in the perceptron the gamma we have na W transpose x equals to W transpose x
uh
y equals to gamma, the
yeah.
margin. So what should the structure? So visually I was getting that the structure should be linear. Of course, it should be a line.
Just
that
one.
should it should be a line that should like create the gap between the classes in the middle, in the origin. So the structure will be linear or non-linear.
Just 1 second. I'll answer that.
Hmm.
Yeah.
And in
So
continuation to that,
yeah,
sir, one
yeah,
more important question I was not getting clarity for that.
yeah.
That why it is said that the logistic regression
Hmm.
can severely exhibit a overfitting on linearly separable data. Actually, I was not getting this.
Yeah, I will have to think about the second question. The first question, though, we have seen this again and again since MLS actually.
Hmm.
He basically, if you do like a data transformation,
Hmm.
so if you do a feature transformation, right, that's what you've learned it as,
Hmm.
then the linear model fits, if it's a linear algorithm like linear regression or SVM, then it fits a linear model in that higher dimensional transform space. But in the original space, it's actually a nonlinear model. So it's like that. So it's if you do a feature transformation, right? So if you have X and Y, you do a feature transformation which adds the features X square, Y square, and XY. So in this higher dimensional feature space, the original feature space was R2, this new feature space is R5. It still fits a linear plane in R5, right? So that's still there. The linear algorithm is doing just what it does. It's doing a linear thing. But
Hmm. Hmm.
this is essentially tricking the model because in the lower dimensional R2, right, the the plane that it fits in R5, that will actually be a curve in R2 in the lower dimensional space. So therefore, this is called the kernel trick. Linear model will only do a linear thing, but you can augment or modify the data set, right? Add some features, do this feature transformation, such that it does the linear thing at in a higher dimensional space. But in the original lower dimensional space, it's a non-linear decision boundary.
Okay, in the
Same as
original.
what we did. Same thing we are seeing again and again. What for PCA, for this linear regression where we do this feature transformation. This
Hmm.
kernel trick can be applied more or less in everywhere where we can do this feature transformation, right? So that it does a linear thing in a high dimensional space, but in the original lower dimensional space, that translates to the non-linear thing that we wanted, right? A non-linear decision boundary or a non-linear best fit line, and so on.
Okay, so these are not
Yeah,
that non-linear structures, but in higher dimension we are.
they are linear. Yes,
Okay.
exactly, exactly. So it could be that, for example, just a quick, you have x, y, x square, y square, and xy,
Hmm.
right? So the weight vector, let's say, in that higher dimensional space is all ones.
Okay.
One, 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 one. Okay.
Hmm.
So that, you know, that will give, so that's a weight vector in a high dimensional space that will give a linear separating hyperplane, right? The hyperplane perpendicular to this weight vector in R5.
Hmm.
Agreed?
Hmm.
Right? But if you write out the equation, right? X plus y plus x square plus xy plus y square is equal to 0.
Hmm.
This is the equation of a curve in R2.
Like it's not the equation
Yeah.
of a linear function. Hmm.
So we got a curve in R2, which is what we wanted.
Hmm. Hmm.
Yeah.
Okay, so the thing that linearity, what we talk about linearity,
Yeah.
so basically it is something related to W.
Uh,
Something
eh, yeah. Can you come again?
like is
It's
it
it's
something like
related. It's yeah. It's I think I got the question. So it's related to. Uh, I mean, it's related to the factor that the hyperplane, the separating hyperplane, right? how to
Hmm.
say,
Okay.
subspaces is it's related to the fact that vector spaces are linear. It's the technical term for this is flats, right? So vector spaces are flats.
Okay.
A straight line is a flat, right? A
Hmm.
2D plane is a flat. And if I had some 3D subspace in, let's say, 4D or 5D, it would be a flat. It's flat. You can think of it as convex also, right? Convex is like how should I say, closed flat, right? Whereas vector space is an infinite flat. Convex means what? You connect 2 points, and if you connect 2 points with a straight line, the straight line falls in the thing, right? Like a polygon. If you connect two vertices of a polygon,
Mm-hmm.
the connecting line is also inside the polygon, right? So that's convex.
Okay.
Agree?
Convex. Yeah.
Agree? So that's what makes a polygon a flat versus let's say like a crescent kind of moon kind of thing, crescent moon, right?
Mm-hmm.
If you connect like the two tips, right, the connecting line is not inside, right?
Two tips. Okay. If it is from above,
Agree?
like some A shape or
Yeah,
something.
some S shape or some V shape, right? Exactly. These
Hmm.
are not these are not convex, right? So a vector space is polygons are like a finite convex. Vector spaces are infinite convex,
Okay.
right? But vector spaces are convex, right? Vector spaces are closed under addition and scalar multiplication. Agree? So that's
Hmm.
convexity,
Okay. Hmm.
right? So vector spaces are flats that way. So vector spaces are cannot be curved. A curved plane, like if I like take a plane and I bend it like I don't know, some metal sheet or something, then
Hmm.
it's not. That thing would not be convex, right? The bent plane would not be convex. So vector space infinite convex. In other words, they are flats. Right?
Let's.
So by linear, they are actually referring to this linearity or flatness of vector spaces. So W transpose X is equal to 0 always defines a vector space. So it always primarily defines a flat, like a convex flat vector space. It
Mm-hmm.
just so happens that we can trick it into getting what we want. It's still giving us a flat, but we can trick it and reinterpret it to get something non-linear or non-flat, basically a curved decision boundary in this lower dimensional space.
Oh, like in the lower dimension space.
Yes. In the higher dimensional space, it's still flat. It's
But
still it's still convex.
so in high dimensional space, it will
Yeah,
exactly do what it meant to be. Like for like
exactly, exactly. What
mm,
it does, the linear model does
linear model.
the linear thing, right?
Linear
It
thing.
gives us a linear decision boundary, gives us a linear separating hyperplane, a subspace.
Okay.
Yeah.
Mm.
Yes, Saladan, is that clear?
Yes. Like
Okay.
I haven't got it like with, with the crystal clear thing, but yes, I
Yeah.
think this topic is something that I have to work on more. Like,
But just keep this example in mind. Right? I'll
hmm.
just recap that example. You
Uh,
had features x and y. Okay. You
hmm.
transformed it to x, y, x square, and xy.
Hmm. Hmm.
So the original was R2, the new one is in R5. Agree so far?
Yes, so somewhere we have lost the linearity with regards to the features we had. So,
Right. But
mm,
in the higher space, right, the linear model does not know that the third feature is actually the square of the first feature. So
mm,
in the higher space, x is just f1, y is just f2, x
okay,
square is just f3, and so on.
like this is the place
Yeah,
somewhere which opens the doors for kernel. Like this is where kernels come.
essentially,
Mm,
essentially, yeah.
mm,
This kernel trick is all. That's why it's called a kernel trick, right? It's modifying the data set so that the linear model still does a linear thing, but
mm,
the model doesn't do anything different. But we are getting what we want out of it, which is something non-linear,
mm.
essentially. Okay. Any
Yes.
other questions?
That one, like you can that first question that you will look up to, and the last one that logistic regression can severely exhibit overfitting on linearly separable data.
Right. So this logistic regression question, I have to look it up. Uh, I'm not.
And the first one that we discussed, that
Yeah.
the margin bound decision boundary on the y-axis, that one.
Okay.
I'm scrolling if I have some, or like.
Okay. Okay. Okay.
Hmm.
All right. Alodhan, while you find the question, just allow me a couple of minutes. I'll be right back.
Sorry. Yes.
Okay. Hello. Hello there.
Yes, sir.
Yeah.
So I've asked my doubts, like, and I have other doubts.
Okay. Yeah. So Kamlesh, Arpit, Videsh, if you have any doubts, I can help you with.
No, sir.
I
Thank you,
had
sir.
that same perceptron doubt which Alauddin asked.
Okay. Okay. But it's clear now, right?
Yeah.
Okay. And Videsh, if any doubts, otherwise I can close the session early today.
No doubt, sir. Thank you.
Okay.
Thank you so much for your
All
time.
right then. Yeah. Yeah. Most welcome. Thanks for attending. I'll see you in the next.
Yeah,
Take care until then.
Good night, sir.
Bye.
yes, sir. Thank you. Good night.
Good night.